Hello everyone and welcome to Positive Delta. Now I want you to imagine that you are taking a stroll through your neighborhood in a sunny afternoon and then you look up at the sky and you see a batch of clouds just floating by giving you company. Now you start to wonder, what if another life form on TRAPPIST-1e, an exoplanet which might have life, is also looking up at its own sky and staring at its clouds? This trail of thoughts then leads you to this video's question, and we will be discussing a very interesting paper related to this question near the end of the video. So let's roll the intro, see what the question is, and start talking about it. First, let's understand what exactly clouds are. This will help us understand the context even better. Now, Wikipedia gives this definition, which might seem a bit complicated, but don't worry, that's what I'm here for, to help you understand. Now, clouds are basically a collection of frozen crystals, liquid droplets, or any other particles that are light enough to be suspended in the air by being uplifted by the air below them. Now, clouds could be made of any type of particles. For Earth, those particles are basically water, both in liquid and solid form. For Mars, they are mostly carbon dioxide and ice. And for Jupiter, it's ammonia and ammonia hydrosulfide. So, depending on the planet, we have different types of clouds. Now, how are clouds important to study of exoplanets? Believe me, they are very crucial, especially when we are producing different spectra, such as transmission spectra or reflection spectra. I have already explained how to produce transmission spectra of exoplanets in this video here, when I talked about the first detection of a chemical species in another exoplanet's atmosphere. Please check it out because it's a very interesting concept by itself. I will be leaving a link in the description down below or a title card somewhere here for you to access it easily. Now, before going ahead, I would like to explain a very interesting concept to you, which will not only help you understand this video better, but also will help you understand these questions of everyday life better. Now, according to quantum mechanics, light is both a particle carrying energy called a photon and a wave where two fields, the electric field and the magnetic field, are oscillating or moving up and down in a periodic fashion perpendicular to each other and perpendicular to the direction they are propagating in. Now, for this video, we will primarily focus on the electromagnetic wave. So let's put the photon away and just study this wave. Now, these points here are called the peaks of the wave, and these points are the troughs of the wave. The distance between two peaks and two troughs is called the wavelength of the wave. Now, these properties are very general for any kind of wave, so you can use it to study sound waves or a ripple in a pond of water. Now, let's consider a scenario where light with wavelength lambda is traveling towards a particle whose diameter is d. Now, in 1871, Lord Rayleigh, in a series of papers, showed that if the particle is smaller than the wavelength of the light, that means d is much lesser than lambda, then the probability that the light will interact with the particle and get scattered off in a different direction is given by this formula here. Now, I know there are a lot of terms in this formula. We can discard the ones that we don't need and we can just simplify it to this equation here. This is a very interesting result. On the left hand side, we have the scattering cross section, which is the probability that the photon will interact with the particle and get scattered off in some other direction. And on the right hand side, we have the wavelength of the light in the denominator raised to the power of 4. Okay, so we have a bunch of symbols on our screen, and you might be asking, so? Well, this is why the result is so interesting. If we increase the wavelength of the light that's approaching the particle, then the probability that it will interact with the particle and get scattered off decreases rapidly. On the other hand, if we decrease the wavelength, then the probability increases. This is an inverse relationship, and you can just look at the plot here and see how rapidly sigma varies with lambda. And now I hope you are able to appreciate the beauty of this equation. The wavelength range of the entire electromagnetic spectrum is huge, from meters all the way to picometers. But the wavelength region that we can see, that is the region of the spectrum that our eyes can absorb, is very narrow. It's only here from 400 nanometers to 700 nanometers, and the famous Vibgyor, the rainbow color scheme, is spread out in this region itself, with blue being on the shorter end and red being on the longer end. A quick question, have you ever wondered why our eyes can see only that particular region of the EM spectrum? Comment down your thoughts below and subscribe to the channel to get notified when I release a video regarding that topic. Let's bring back our equation. Now we can see that when light with shorter wavelengths or at the bluer end of the spectrum is traveling towards a particle, then the probability that it will interact with the particle and get scattered off is very high. Please note that this is a probability. It's not 100% sure that it will interact, but the chances of it interacting are very high. On the other hand, for light with longer wavelengths or at the redder end of the spectrum, the probability or the chances of it interacting with a particle is very low. Now we can answer the question that I had posed a while back. The reason the sky is blue because during that time the sun is at the zenith position and the dust is be able to effectively scatter of blue light more than the red light. That's the blue light that reaches our eyes eventually. The reason why sunsets and sunrises are red is because the sun at that time is at the furthest distance from us. So the light that eventually reaches us mainly comprises of red light since the blue light is already scattered off. The reason why stop signals are red is because you need to be able to see the signal from a far distance so that you can stop yourself in time. This entire phenomenon, where the probability of scattering of light depends on the fourth power of the wavelength of the light, is called the Rayleigh scattering. Now let's get back to our discussion of clouds in exoplanet science and see how this phenomenon is applied there. Now let's look at this plot here, which are reflection spectra, not transmission spectra. Reflection spectra are the variation of the intensity of the light that is reflected from the exoplanet surface itself. This helps us probe deeper parts of the atmosphere. Now there is a lot of information packed into this spectra and I cannot afford to unpack everything and explain to you in this video itself. So I will be making another video about the different types of exoplanet spectra that is used for studying these planets. So like this video and hit the subscribe button to get notified about such a video dropping soon. So the x-axis here is the wavelength region and the y-axis is the planet flux to the star flux. Basically, if the light from the planet is more, then the y-axis value will be higher. It's as simple as that. Okay, so now let's look at these two plots here, the yellow one and the green one. We can see that the y-axis values for these two plots here are a bit higher. Now let's just look at the wavelength region here and we can see that it's at the shorter end of the region. This is Rayleigh scattering at work, which we were just discussing a few minutes ago. Now just let's construct a flowchart to understand what actually is going on here. First, there is more flux from the shorter wavelengths in the wavelength region. Second, this means that there are more shorter wavelengths getting scattered off. Third, this is a classic scenario of Rayleigh scattering. And fourth, Rayleigh scattering happens only when there is dust particles in the atmosphere, not cloud, because the particles of the cloud have the similar size as the wavelength, so they do not follow the inverse relationship. So if there is cloud in the atmosphere, then that region of the spectrum will be flat, as can be seen in these two spectra here, whereas the other spectra have a steep increase in the flux, which means the dust particles are scattering off the wavelengths effectively, thus giving an example of Rayleigh scattering. I was blown away when I studied this concept because with the help of some measurements coupled with some amazing physics, we are able to detect clouds on some other planet millions of kilometers away. Of course, these are similar to spectra, but we have been doing it for real while studying multiple exoplanets. One conclusion can be immediately drawn. A cloudy planet is brighter than a planet with a clear atmosphere. Clouds also decrease the depth up to which photons can penetrate before reaching us. So even though detecting clouds on another planet is pretty cool, it does prevent us from studying the planet's atmosphere in much more detail. Wow, we have discussed a lot about clouds. Thank you so much for sticking with me till this point here. Please like this video and subscribe to the channel if you found something very interesting and got to know more about the world. Let's move ahead and discuss a very interesting paper related to these clouds. In 2013, Laura Carried from the University of Chicago, in collaboration with other scientists across multiple institutions, published a paper confirming the presence of clouds in the atmosphere of GJ1214b, a super-Earth that's orbiting GJ1214, a red dwarf star that is 48 light years away from us. A super-Earth is basically a planet that is larger than Earth but is smaller than the gas giants present in our solar system. This planet particularly is 2.7 times larger than Earth and 8 times heavier than Earth and is the best known candidate for being an ocean planet. The team observed the planet using the Wide Field Camera 3 of the Hubble Space Telescope. They observed the planet and obtained light curves from 1.1 to 1.7 micrometers in 4 separate observations. These are the spectrophotometric data of the observations. The dots represent the data points that they have collected, and the lines represent the theoretical models that best fit the data. The different colors represent the different wavelength bands in which they have collected the data in. Okay, so now let's understand this plot here to appreciate the conclusion even more. The black dots here represent the data that's collected by this team, and the grey dots here represent the data collected by other teams in some other previous work. The orange line here represents an atmosphere which is very similar to our sun. That is primarily hydrogen and helium and trace elements of heavier elements such as oxygen and carbon. The blue line here represents an atmosphere which is 100% water. So clearly these theoretical models do not match the data that they have collected. Now let's zoom in to this region that they have observed in and check for other theoretical models. The green line here represents an atmosphere with 100% methane composition, while the red line represents an atmosphere with 100% carbon dioxide composition. So clearly none of the theoretical models match the data that they have observed, thus confirming their conclusion that there are clouds present. Clouds block the light that's coming from the star and passing through the atmosphere, and this then blocks any spectral features that might arise from regions below the clouds. Oh, and you might be wondering why they construct atmospheric models of certain chemical species. Well, there are two main reasons for this. The first one is that these molecules are expected to be present in the atmospheres based on the evolution history of the planet, which determines the physical properties of the planet, which then determines what chemicals will be present in the atmosphere. The second one is that the wavelength region that they have observed in. As I had explained in this video here, each chemical species exhibits spectroscopic features in particular wavelengths in the EM spectrum. So the wavelength region that they had observed just happened to be the region where these molecules would exhibit their features in. And that is the end of today's video. Thank you so much for sticking with me through to the end. I knew it was a bit lengthy one, but I had to explain the underlying physics principles so that we can understand the physics and the paper better. I hope you learned something new about clouds and enjoyed watching this video. And I truly hope you are able to appreciate the beauty and simplicity of the physics involved here. Leave your thoughts and questions down below in the comment section. Please like the video and share it with your friends and family, and please subscribe to the channel because your love and enthusiasm for science keeps me going. Thank you, stay curious.